Okay, so in this lecture, we're going to be continuing on with Chapter 2. I'm going to talk about 3 different kinds of bonds, and I'm going to talk about electronegativity, as well as circling back around to some of the notation that we use in chemistry. So, chemical bonding, chemicals often bond with one another, and most of the time that is to fulfill their valence shells, like we talked about last time with the octet rule, right? They're trying to get a full valence shell, whether that means giving electrons away or picking up other electrons from elsewhere. So, again, electrons are the most important particles, the most important subatomic particle when we're talking about atoms interacting with one another. Electrons have those distinctive energy levels I was talking about earlier. Remember, the first one has 2 electrons will go there, and then 8 in subsequent shells. Atoms react with one another because they want, and that's in air quotes again, they desire, in air quotes, to become more stable. They want to be as stable as possible. Okay? And the reason for that is just kind of because unstable things don't last in nature. If you take, like let's say you were to go outside and take a stick and balance it so that it was just standing perfectly still, it's not going to stay that way. That's an unstable configuration. That stick is ultimately going to fall to the ground. In the same way that atoms that are unstable, that have an unfulfilled octet, are going to bond with one another in order to form a more stable configuration. Okay? So if you have a full outer electron shell, you're going to have more stability. Non-reactive elements, like inert gases, have full electron shells, and so they're not going to react with anything. Other elements that are reacting in order to complete their valence shell after they've done that usually will be fairly non-reactive. So, again, the whole point of this is electrons or atoms want to have a filled up valence shell, and in order to do that, they are going to bond. They're going to form bonds with other elements, with other atoms. So this is a bit of a messy diagram. It's from your textbook. So hydrogen and helium are not, hydrogen is not stable because it does not have a filled outer shell. And if you've ever seen a video of the Hindenburg, you will know how unstable hydrogen is. Helium, on the other hand, does have a filled outer shell because it has 2 here, right? And that you can only fit 2 in that first valence shell is what I've told you. So helium is stable. If you want proof of this, go pop a helium balloon, or put a lighter on a helium balloon, it'll just pop. Put a lighter on a hydrogen balloon, it will explode. Okay, this one is not stable. This one is quite stable. This one is not reactive. This one is quite reactive on the left. This one is not reactive. Carbon, wants to fill up its outer shell. How many electrons do we have in the outer shell of neon? Let's count them. 1, 2, 3, 4, 5, 6, 7, 8. So pause it really quick after I ask this question, but will neon react with anything? Will neon easily react with anything? The answer to that question is no, it will not react. Neon has a filled up outer shell. It's not going to make chemical bonds easily. It's not really going to do much. Same thing down here with argon. Let's count these valence electrons. 1, 2, 3, 4, 5, 6, 7, 8. It's got a filled valence shell. Argon is indeed a noble gas. It is not going to react. Whereas sodium has one valence electron in its outer shell. Okay, so sodium is going to react. Why? Because it wants to fill up its outer shell, because that is the most stable form that an atom can have, a filled valence shell. So, talking about some notation issues here for a minute. This is a molecule called methane. It is CH4, and its electron pairs are depicted as these little lines. So, electron pairs here are depicted as dots. It's a little bit easier to see them here because you can see both electrons, dot, dot, and you can see that carbon has, indeed, 8 electrons in its outermost shell. You can also see that each of these hydrogens has 2 electrons in its outermost shell. We're going to talk about that shortly. These two diagrams show the same exact thing. Okay? This line is representational of an electron pair. Okay? This line represents these electron pairs. It's just that chemists got a little lazy with the notation. And there's a lot more ways that chemists have gotten lazy. If you continue on taking a ton of chemistry, you get to organic chemistry and they just start drawing lines all over the place. But it's neither here nor there. These lines represent these electron pairs. So again, you saw a little bit of this in the last video. There's more than one way that you can write a molecular formula down. So you could just write NH3 and everyone would basically know what you're talking about. Just write NH3 down. Another thing that you can do is you can write down the structural formula. And these are not the only 4 ways, by the way. There's more ways you can do this. The structural formula just tells you some more information than you had with the molecular formula. You have these 2 electrons here, and then you have these 3 hydrogens bonded to this nitrogen like this. Okay, if you get to the ball and stick model, you no longer see that electron pair that was out here, but now you're seeing more about the geometry of the NH3 model. And when you get to a space-filling model, you see even more. You see the geometry of the molecule, but you also see the relative size that each of those elements occupies. It's called a space-filling model. Probably don't worry about the specifics of these things. They're just things that I want you to have seen. I wouldn't ask you to draw a space-filling model. I might not ask you to draw a ball and stick model either. You may be asked to understand how these structural formulas work. And you're definitely going to want to know molecular formulas because they're obvious. I mean, NH3 means 1 nitrogen, 3 hydrogens. So kind of moving along with this idea of chemistry notation, this is 1 carbon. These are 4 hydrogens. Okay, this is CH4 over here. This is methane. And this arrow means yields. Okay, so 1 carbon plus 4 hydrogens yields methane. And this yields thing, this just kind of means like a chemical reaction has taken place. And we've converted our reactants. So your reactants, that's going to cover it, but your reactants are what is on the left side of the arrow. And your products are what is on the right side of the arrow. Okay, so reactants, these reactants undergo some sort of chemical reaction, yielding our product, or sometimes products. So reactants yield products. Carbon plus 4 hydrogen yield methane. So moving on to bonding, which, by the way, this is a particular kind of bonding. Here, these hydrogens with this carbon are all bonded together. But the first kind of bonding we're going to talk about is covalent. So co, sort of meaning together, valent referring to valence electrons. So in covalent bonding, elements share electrons with one another so that they can both have full outer shells. So the idea here is they're sharing something so that they can both get to a more stable configuration. If you took 2 hydrogen atoms, your products, and you put them together, you would yield H2 because they are sharing that outermost electron. Okay, here's hydrogen, you put them together to form H2, which is more stable than those hydrogens by themselves. Water is also an example of covalent bonding. These hydrogens are going to share their electrons with this oxygen. Okay, this is another example of covalent bonding. Again, covalent, you should be thinking, means shared electrons, covalent. So still of covalent bonding, we have two different kinds of covalent bonds that you can have. We have nonpolar covalent and we have polar covalent. And the reason we're talking about this within the scope of biology is because this is going to affect hugely the behavior of these molecules. Whether or not something is polar or nonpolar is a really big deal, as we're going to find out later on in the semester. So be cognizant of this. Understand that there is a big difference between a nonpolar thing and a polar thing, and the reason for that lies within the chemistry. Okay, so here is a polar water molecule. Definitely know that water is polar. That's a really big deal. And you see here you have these hydrogens down here, and you have this oxygen here. So I referenced this previously, but I'd like to go into a bit more detail now. Hydrogens and oxygens have a big difference in their electronegativity. And electronegativity means how much that particular atom wants to pull on the electron. Electronegativity means how much an atom wants to pull on the electron. Okay? And oxygen is more electronegative than hydrogen. And so this oxygen is going to pull those electrons toward itself. Again, because it is more electronegative. The reason it's more electronegative, you have to get into physics and some chemistry to really understand that, and it's not super important to know why it's more electronegative, but you should know oxygen is more electronegative than hydrogen, and it's pulling those electrons toward itself. And so when it's pulling those electrons toward itself, it's making itself slightly more negative than these hydrogens. And so that's what this little D minus represents up here. This little D minus represents a region of electronegativity. Because the oxygen, again, let's go through the logic here. Oxygen is more electronegative than hydrogen. Oxygen wants to pull those negatively charged electrons toward itself. The result of that is you wind up with an oxygen that is more negative than the hydrogens that it is covalently bonded to. Right? So you wind up with a region of negativity here and a region of slight positivity, slight positive charge around these hydrogens. Let's talk about for a second a nonpolar covalent bond. So here we have carbon and here we have hydrogen. Okay, this is methane. We've talked about methane a few times in this lecture already, CH4. You wind up with carbon being slightly more electronegative than hydrogen. There's not a big of a difference as there is with oxygen. And if you take chemistry, you'll probably wind up calculating these things. They'll give you a table that tells you how electronegative everything is. I'm not going to worry about that right now. But carbon is slightly more electronegative than hydrogen. Right? And so it's drawing more electrons toward itself. So why isn't CH4 then a polar molecule? So polar means you have differences in charge that exist within it. The reason that CH4 isn't a polar molecule is because it is symmetrical. It has 4 hydrogens all around it in a symmetrical way. And so, yes, it's pulling all those electrons in toward itself, but you have 4 regions of positivity that are equally distributed. It's kind of like if there was a set of quadruplets and they were all pulling on a rope all at the same time, or if you had a set of people that were of the exact same strength pulling on a rope at the same time, it's not going to go anywhere, right? You're not going to notice this region of charge. And so that is why CH4 is a nonpolar molecule. So, again, there is a spectrum of electronegativity with fluorine being the most electronegative. I'm not really as worried about that for you guys. I just want you to know what is electronegativity, what is its role in covalent bonding, and what is its role in forming a polar versus a nonpolar covalent bond. The next kind of bonding, and actually I guess before we move on, let's say we had a molecule like H2, right? Or O2 even. Diatomic oxygen. What's the difference in electronegativity between oxygen and oxygen? There isn't one, right? And so O2 is not going to be polar. It's going to be covalent, but it's not going to be polar because, again, neither one of those molecules is more electronegative. So you have kind of two options for a nonpolar covalent. You either have the same amount of electronegativity or you have symmetry, like this CH4 molecule. And again, you guys, please be reading your book. And when you're checking out these lectures, if you aren't understanding something, send me like a timestamp and ask me what I'm talking about. So you'd be like, hey, Aaron, in this video at 15 minutes and 52 seconds, what on earth is going on? I didn't understand you. I'm not sure. Anyway, moving along. We have covalent bonds and we also have ionic bonds. And in an ionic bond, one of the atoms is much, much more electronegative than the other. So in an ionic bond, one atom is much more electronegative. And so what happens is one of those atoms steals the electrons away. It just takes all those electrons away. Just grabs them up. So in the case of NaCl, which again is table salt, chlorine is much more electronegative. Chlorine really, really, really wants to have that electron. And so what does chlorine do? Well, it goes to sodium and it grabs poor sodium's electron. Chlorine grabs sodium's electron. What happens to chlorine after it grabs that electron? Well, it becomes more negative. If you grab a negative charge, you yourself become more negative. Well, what happened to the sodium? Think about this. What happened to the sodium? The sodium physically had its electron removed from it. So sodium is subtracting negative charge, which is you're subtracting a negative. It's a weird way to think about it. But sodium's losing a negative charge and chlorine is gaining a negative charge. Sodium is going to become, pause it really quick and think about this and quiz yourself. What's happening to sodium when it loses that negative charge? It's becoming more positive, right? What's happening to chlorine when it grabs that negative charge? It's becoming more negative. So what's happening is that chlorine's becoming more negative, sodium's becoming more positive, and if you've ever heard the phrase opposites attract, it may not be true sometimes in life, but it is definitely true in chemistry. Okay, so that negatively charged chlorine is very attractive to that positively charged sodium. And so they wind up just hanging out together in this ionic bond. Okay, covalent, sharing an electron. Ionic, nope, one element is just grabbing that electron away. They're changing charge and they're becoming attracted to one another. So here's an example of that. You have Na and Cl transferring electrons, becoming attracted, and because of the way these negatives and positives stack up with one another, they form this thing called a crystal lattice. And they wind up forming crystals. Salts form crystals because of these differences in attraction. And you can see why they do that. You can see we have these, these chlorines. We have these negatively charged chlorines, and of course these positively charged sodiums want to stack all around them. And you get those crystal formations because of these differences in charge. Before we move on to hydrogen bonds, I just want to review really quick. Covalent, sharing electrons. You have polar covalent, where one end of the molecule is slightly negatively charged and one is slightly positively charged. You have nonpolar covalent, where there is an equal distribution of charge throughout the molecule. And we have ionic bonds, where one element is just stealing the electrons away. Okay, and there's a lot of charge within ionic bonds. This is going to be important later on when we start talking about solubility and stuff that we'll get to soon. Okay, so the next kind of bond that we're talking about is hydrogen bonding. Hydrogen bonding is incredibly important for you being alive, as we're going to get to later on. But when you have water in a solution, I talked about how you have the oxygen being partially negatively charged. Well, that's attracting hydrogens from nearby water molecules. And that's what's causing this hydrogen bonding. Okay? The partial negative end of one water is attracted to the partial positive end of another water, and that forms the hydrogen bond. Here's a good picture of a hydrogen bond. Each of these is an H2O molecule. And as I said before, you have this oxygen with the partial negative charge. If you don't know why the oxygen has a partial negative charge, go back about 10 minutes. Check that out again. Okay, and you should be able to tell me the term. I want you to know the specific term for why oxygen has a partially negative charge. So again, if you don't know it, head on back, sorry. But you'll see here, oxygen has this partial negative charge, which is, of course, like I said, opposites attract, of course, attracted to this partial positive charge. Okay. This dashed line right here represents hydrogen bonding. And we're going to talk about hydrogen bonding later on. I just want you to kind of fundamentally understand what it is in this video, but it is very important, and it really gives water a lot of its super special properties. It's what makes water very important to your life, to everything's life, actually, and makes it kind of a weird but super interesting, cool molecule. The final topic I'm going to talk about today is free radicals. I'm sorry, there's way too much text here. Basically what happens with a free radical is you wind up with electrons that are not paired up. Okay? Because they are not paired up, they are quite unstable. So free radicals don't last for very long in nature, but what they do is they mess up your DNA. Because they have that negative charge that really wants to find something, it really wants to bond with something that's just out there in the universe, not sure what to do. And that negative charge is going to do stuff like attack your DNA, and it's really bad for you. You can increase the number of free radicals that you have by doing things like smoking. If you're a very, very white guy like me, you can increase the number of free radicals you have by not putting on sunscreen. You can increase the number of free radicals you have by drinking too much alcohol. But there are things that you can do, like eating antioxidants, like eating your blueberries, getting some vitamin C. And what those will do is those will react with the free radicals in a way that's not going to harm your DNA. It's not going to harm your body. So here's a picture of our free radical, nitric oxide. Remember, these are our products. Yields, arrow, this is our reactant. I'm sorry, these are our reactants. I was just testing you. These are reactants, yields, arrow, these are our products. And this is nitric oxide. You have this free, unbound, unpaired electron, and it's going to mess you up. It's going to attack your DNA, mess up your cells pretty good. I think that's about enough for this lecture.